Okay, we'll get started with today's lecture. Let me go ahead and turn down the mic volume here. Okay, so, let's see, is that too loud for everybody? That is like, let's see. All right. So, from the perspective of me as an American, I find, some parts of Europe to be very weird. The same is true for Europeans in the U.S. There's a saying I like where about comparing Britain to the U.S., which is that in the U.S. 100 years is a long time, and in the U.K. 100 miles is a long distance. I would when I was in graduate school, I would regularly take a 90-mile trip to visit my in-laws. Because that's how far away they lived. It's not too hard, not too hard. But it's just from the peculiarities of the way that density is set up in Europe. Now, one of the things that I found interesting about Europe is the existence of microstates. For instance, take Andorra. I'm going somewhere with this, don't worry. Take Andorra, this little country here between France and Spain that you may have not known existed until about 5 seconds ago. It's actually got a very unique form of government. It's ruled by co-princes, one of which I believe is the president of Spain, as our president of France at some point. The other person's one of the bishops. You can check out the Wikipedia article on it. It's very interesting. And the entire notion of that you've got states that are tiny and they exist as independent things. That's wonderful. Now, today we're going to be talking about one of the other we're going to be talking about something called Monte Carlo approximations. Monte Carlo is this primary city. Well, it's city? No. Let's see. Well, it's in Monaco, which, if we zoom in, is another microstate. Very, very tiny, Monaco, and the Monte Carlo Bay Hotel and Resort. Not even a city. It's a casino. But that is what Monte Carlo is known for, and that is what we are talking about, what we are referencing when we are saying Monte Carlo approximation. We're talking about gambling here, okay? Because the fun thing, they never tell you the fun stuff in mathematics when you're a kid, that the entire branch of statistics and probability, that comes out of gambling, which was a side hustle for a lot, and figuring out the odds for the gambling games was a side hustle for a lot of people who did what they considered more serious mathematics. But the entire thing about statistics is this fascinating process. Now, statistics is hard, especially when you get to, Bayes' theorem. That's one of the first hurdles to deal with in statistics, which is the probability of A given B is denoted by this formula. Yeah, the probability of A given B is equal to the probability of B happening given a knowledge of A, or given A is true, times the probability of A occurring over the probability of B occurring. It is a weird, complicated thing, and it is a lot to digest all at once. And that's just like the first step of statistics. Don't worry, they walk you through that in these classes. But we're going to be taking the approach that we want to avoid things that have this many capital letters in it. So we're going to be trying to not do these statistics. We want to not have to work hard at figuring out the probability of certain events. Now, I enjoy doing Monte Carlo approximations in this class because they allow me to basically test pretty much everything but file reading in a single question. File reading and string parsing, I guess. They let me test for loops, while loops, and logic, and function writing. They let me test a lot of things, and they let me ask interesting questions. Now, one of the more interesting things that, so we'll be working on the project in your textbook, link from Canvas. It is, if you go to Runestone and log in, right? If you go to Runestone and log in, we'll take a look at basically our first and possibly most famous question that we see from Monte Carlo, that we're going to be addressing with Monte Carlo approximations, which is confusingly named the Monty Hall problem, which is Monte Carlo, that's Monty with an E, and Monty Hall is a Monty with a Y. Yeah, it's going to be confusing, sorry. The question's already confusing. So we scroll down, you either click on the link in Module 9 for Thursday, or scroll down to here, to Project 12, Monte Carlo simulation. Yes, it's listed under files. Are we going to do the file reading portion of it? No. No. We have plenty of time already. Okay. The idea here is that rather than the entire idea of doing Monte Carlo approximations is that's a fancy way of saying we're going to simulate the problem. And the premise comes from you go to a game in a casino, okay? And you see a bunch of people playing these games of chance, and you have no idea what the odds are for winning, right? You have no idea what the odds are for winning. And to be honest, you're not really that good at math, and they didn't let you bring any pencil and paper because they don't want anybody doing that kind of math to kind of game the system. So in that case, how do you figure out the odds of a system, of a game? And the answer is you just observe the system. You watch other players play it, and you can count the winner. And for some things that are binary, you can count the winners and losers. Or you can watch the total payout. Or you can watch the total payout if you want to figure out what the house advantage is. The amount of money given versus the amount of money lost. Given enough, and the idea here is given enough observations, you will be able to actually see what the win-loss ratio is for a game. That's pretty much it. We're going to figure out hard statistics by not doing the statistics, but by doing the game instead. Simulation's pretty big, and this is probably one of the more easy and abstract ways to do it. Abstract in the sense that we don't really have to, that we're just basically simulating games of chance and don't really have to actually code too much. We will work our way to approximating pi. We've done that already with the Leibniz formula, where we calculated pi over 4. We're going to do the same thing, but with turtles today. Instead, we're going to scroll all the way down to part 3, to the Monty Hall challenge, which is sad that it's been taken off of YouTube, but it's such a well-known problem that we don't actually need a link. Now, the Monty Hall problem is named after a game show hosted by Monty Hall. Monty Hall problem. Okay? Now, the Monty Hall problem is a brain teaser, and it's one of the more classic brain teasers in mathematics from the game show Let's Make a Deal. And the idea here is that behind me are 3 doors. They're not, but pretend they are. Behind me, there are 3 doors. Behind these doors, I have different prizes. I've got 1 car and 2 goats. Now, for the purposes of this problem, this is very important. Okay, this is very important. For the purposes of this problem, we are treating the car as being more valuable than the goat. Okay? Very important that we remember the car is more valuable than the goat. When I present this problem to my wife, she always, she loves goats, so she always goes for the goats. So for the purposes of this problem, we are going with the car. Now, the way this game typically works with cars, goats, cruises, or whatever prize they have, is that Monty Hall will, the contestant will choose one of the doors 1, 2, or 3, okay? And then say the contestant chooses door 1. Then what Monty Hall will do is that he will reveal one of the other doors. Now, we're going to define how he chooses that in a second. And then he'll ask, do you want to switch? Okay? Okay, do you want to switch? So the premise of the problem, as we do it here, is this was asked to Marilyn Vosavant's Ask Marilyn column in Parade, and it was presented as thus. And it's very important that the wording is this, because if you do different wordings, the outcome is different, because statistics are weird like that. Okay? Suppose you're on a game show and you're given the choice of 3 doors. Behind one door is a car, behind the other 2 is goats. You pick one door, say number 1, and the host says, and the host, who knows what's behind the other doors, opens another door, in this example 3, and reveals a goat. So the host will always open the door and he'll always reveal a goat. And he'll say, do you want to switch? Is it in your advantage to switch or to stay put? Now, what do people think? Is it switch, stay put? What are the odds? Yes?
So technically it's one first through one chance, right? If you switch for 1 or 2 chance, it's like switching is more likely,
It is technically better to switch, but you're wrong about the statistics. Yes?
I'd say 50-50.
It is not 50-50. That's the fun part about this problem. Yes?
Don't switch because if you have 3 doors and you choose one door with 1/3, but if you switch it, that means that you have 2/3 of a chance. So that means that you're technically choosing 2 doors instead of 1 door.
That's correct. If you switch, your chance of winning is 2/3. 2 out of 3. This is one of the most counterintuitive kind of ideas in statistics. It's almost one of those paradoxical things. It's very famous. Savant's response was that the contestants should switch to the other door under the standard assumptions, which is that the host will always reveal a goat. Okay, he'll never reveal the car. Then you should switch. Now, and if you switch, you have a 2/3 strategy probability of winning and a 1/3 probability. And this actually caused a huge uproar. Tons of letters came in because email wasn't really a thing yet. Tons of letters came in, basically from people all over, saying that Vos Savant was wrong. And she was like, "No, I'm not wrong. The math is quite clear." It was, approximately 10,000 readers, including 1,000 with PhDs, wrote the magazine, most of them calling Savant wrong. Even when giving explanations, simulations, formal mathematical proofs, many people did not accept that the best strategy is switching. And Paul Erdos, who's basically, he's so prolific that we have a number called an Erdos number, which is essentially the mathematics equivalent of your Bacon number for actors. That is how prolific he is. 6 degrees to Kevin Bacon is what I mean by the Bacon number. How many degrees of difference do you have before you've acted with Kevin Bacon? Paul Erdos, he published a ton, and he remained unconvinced until he was shown a computer simulation, e.g., a Monte Carlo approximation. The solution is so counterintuitive it can seem absurd. It is mathematically closely related to other paradoxes. Mathematical paradoxes are one of my favorite kinds of things. I enjoy, if you are interested in other paradoxes, I highly recommend the Simpsons paradox, which is not about the Simpsons, I don't think, but instead about basically how an aggregate of data can give misleading statistics. Now, the reason for this is that if we have some simple solutions here, right? We've got, if you initially choose, so the easiest way I find is this diagram over here. We have 3 doors, okay? We have 3 doors. You've got a goat, and a car. So if you use the switch strategy, right? If you use the switch strategy, then if you choose a goat, the other goat's going to be revealed. So if you choose the first goat, the other goat gets revealed, and you switch, and you win. If you choose the second goat, the first goat's going to be revealed, and you switch and you win. So that's 2 of your 3 initial choices. If you choose your car as your first choice, one of the 2 goats is going to be revealed. Doesn't matter which one, and if you switch, you lose. And why is this? Because it's that whole Bayes theorem that I went back to, which is not the probability that you chose, but the probability that let's see, I think they have it here. It is not the probability that you just simply chose the right door at the first time, but let's see. Where is that? Control. Do they not have the Bayes theorem? Oh, yeah. They do somewhere. Bayes theorem. So it goes into that about this, which is what the odds that the odds given that they've hosted the other door. Now it's weird though, being able to see, I can explain this to you, but it's very hard to kind of see it. So what we're going to do is that we are going to simulate this to see what the odds are of winning this game. Now we're going to make some assumptions to make this easier for us, which is that if you think about it, choosing one door versus another, if everything is shuffled around at random, then choosing one door is no more likely than any other door, right? So in other words, I'm always, just for the sake of simplicity, I'm always going to choose door 0 as my initial choice, door 1, index 0 as my initial choice. But that's just to make things easy. Now, Monte Carlo approximations, as I've alluded to, I love doing them because they allow me to test things. So that's a major hint that this is going to be on the exam too. And this is also a major hint that it's going to be one of the options for a question on the final. It's always been, so Monte Carlos are something that I really love doing. So how does this look in practice? Well, my first step when I'm trying to do a Monte Carlo approximation is that if we're playing a game, I write a function to simulate a game or a turn, depending on what kind of thing we're doing. So we need to simulate a game or a turn. Here, it just makes sense to simulate the entire game, right? We can add in an argument later if we want to, but for right now, we're just going to keep everything localized to creating a game. So what are our pieces in the game? The pieces in the game are our doors. So I'm going to create a list of doors, and I'm going to create a list of what's behind them. I'm going to simply use C for car and G for goat. And once again, I would like to remind everybody that the car is more desirable than the goat in this instance, right? So here we go. We've got a car and we've got our goat. Okay? So there's our doors. And what we're going to do is that we're going to really make use of the randomness library in this one. We haven't really made too much use of random before, but now, because we're dealing with randomness, we're really going to make use of the random library. Import random. Okay. Random is is full of a lot of useful functions. You can use it to generate dice rolls by just generating a random number. You can use, as we'll see, you can randomly pick things out of a selection. Here, what we're going to do is one of the more useful things built in with Python, which is that given a list of things, I'm just going to scramble that list. I'm going to treat it like a deck of cards and shuffle it. So here, what I would do is random.shuffle doors. Very conveniently named function. And what that's going to do is, I'll show you what it's going to do. Print doors. Not print doors. Yeah, print doors. And then I'm going to just run the game here. Okay, just simply to show you that it's going to work for a bit. Okay, C, let's see. CGG, sorry. GCG, so each time I'm getting a slightly different response. Here I'll go ahead and just make it clear, goat 1, goat 2. It doesn't really matter which goat is a goat. They're all, the two goats are fungible, but here we can see it in more detail how it gets shuffled. Every single time I hit save and run, it's giving me a different outcome for that. Make sense? So random.shuffle is pretty useful here for making sure that we can basically simulate a game and decide whether or not we're going to win or lose. Okay. let's see over here, random nut shuffle. So now what we can do is that we can do an if-else statement based on, what we're going to do is we're going to make our choice. We're going to select, the players then selects their door. We could choose that at random. Honestly, though, that's going to make things slightly more difficult if we do that. But statistically, it's going to be the same whether I choose the first door or any other door, right? So if I choose door 0, it doesn't really matter. And I'm going to make that choice, okay? My choice is equal to door 0. And we could always modify it later to see that in more detail, right? So if choice is equal to 0, if choice is equal to so if we chose a goat, right, that means that one of the other ones are a goat. So if, and I'm just going to go through this in probably more detail than I need to, or more depth of a simulation than I need to, but it works. If doors, yeah, it's doors, not door. Doors 1 equals goat. This is where we could implement our strategy, right? So I'm going to go ahead and I'm going to go ahead and do in my first argument. G equals switch. So I just did something up there that we really haven't seen before. This is called a default argument. Okay? So I've passed in an argument. So first off, the first part of it is that it's no different than me saying it takes an argument called strategy. If I say strategy is equal to switch, this is called a default argument, meaning that if I don't pass in a value, then strategy's value is going to be switch. But if I do pass in a value, it's going to be whatever it is. So in other words, what's really cool now is I can give this function either 0 arguments or 1 argument. It's pretty cool. When I call it, I can either leave it empty or I can put in a parameter. So here, what we're going to do, if door is equal, so if choice is equal to, if we chose a goat, if the door is equal to 1, and strategy equals switch, right? String that. If the strategy we chose was switch, then we will, so this is reveal door 1, find a goat. Then we'll say that our choice is equal to door 2, right? Else, or elif, was stay. Actually, no. I don't have to even put in stay, because if my strategy is stay, I'm just not changing it, right? If doors 2 equals G and strategy equals switch. So that's if we reveal door 2, door index 1, reveal door index 2, then the other door is door 1, so we're going to say choice is equal to doors 1 And now we have to deal with what if, oh, no, that's if my right. So if my choice is a goat, then he's going to reveal the other goat, right? If my choice is a goat, he'll reveal the other goat. Else, my choice was a car. Otherwise, my choice was a car, and then he'll reveal one of the goats. So, and there's no choice involved here. Strategy equals switch doors. Choice equals. Okay. Now again, what we're doing here is we're just choosing door 0 just because we can. And it's going to just, because the statistics for choosing randomly from each door versus just always choosing door 0 is always going to be the same. Each door is equally likely to have something behind it, so might as well make it easy for us and just choose the first answer all the time. Okay, if we chose a goat, we wouldn't know that, but Monty would. Then he'll reveal the other door with a goat, and we'd switch. Otherwise, he'll reveal door 1 or door 2. It doesn't really matter, but we'd switch to away from our initial choice. And now, what I'll do is I will finally, now that we've played the game, for Monte Carlo approximations, we basically return one of two things. If we're just simply doing a win-lose kind of option, then we will just simply return true or false. If we're simulating something like dice rolls and want to figure out, some kind of average score, then we'd return that. If we're trying to count the number of turns something would take, then we might do something like that. So return. So here since we either win or lose, we're going to basically return choice equals car. Let's see. Okay, and save and run. If strategy is yeah, it would help if I could spell strategy. Where did I misspell it? There. Okay, save and run, and we get nothing back. Because of course I don't call it, but the point being is that I wanted to make sure I run it first. So print game, right? And if I run it, let me zoom this up. If I run it, it says true, false, true. And just hitting it a bunch, it looks like I've got a bunch of trues more than false, but that doesn't actually mean anything. I could just be highly lucky. I like to think I'm pretty lucky. And so the strategy is just by default switch. Now, if I wanted to change it to something else, like stay, I would just simply do stay, and we can see the results of stay. But here we've simulated the game. Now we actually have to do the Monte Carlo approximation where we count the results to find the statistics. So I like to call this trials. Basically, when I make something capitalized in a programming language, the convention for this is basically saying, hey, this is a constant. If you use this, don't change it. If you use this elsewhere, don't change it. It should only be changed like right here when we declare it. So we're going to do 1,000. 1,000 what? 1,000 games. Here, and I will share this code with you so you can take a few minutes to look at this afterwards. For in range trials, why am I just not writing down 1,000? Because I'm going to use trials multiple times, and if I want to change the number of trials, I'm going to have to change trials. I'm going to have to change the one number in a lot of places. Result is equal to, sorry, result is equal to game. Okay? And now the other part of it is that, so we're going to play the game 1,000 times and we're going to store the result. Now, what I'm going to do is I'm going to say wins is equal to 0. We're going to count how many times we won. Result is equal to game. If result equals true, in other words, if we won the game, wins plus equals 1. No need to keep track of the losses, because the losses is just simply trials minus wins, right? No need to keep track of losses here. There's no harm in doing so, but there's also no need. And then print wins over trials, okay? In other words, that would print out the number of times I played the game, the number of times I won at the game over the number of times I played the game. In other words, our win percentage. So if we run it now, 64, 65, 67, 67, 68, 62, 67. It's a bit swingy at the moment. But again, we're dealing with randomness here. And random isn't always going to be, and when you grab a random sample of things, you're not always going to get like a purely evenly distributed sample size. But you can avoid that by doing larger samples. Like instead of doing 1,000 games, let's go ahead and run 100,000. And the computer really doesn't, well, I guess 100,000 is a bit much. Oh, there we go. Don't do a million. But there we go. Now the answer is a lot more accurate, or a lot more of what was hypothesized, which is 2/3. Right? 2/3 chance of winning if you switch. Okay? I think I'm going to delay doing the mathematically inclined part up above this and instead go for something to keep you more interested. Okay? So let's go ahead and give you a game, another game. Okay? This is where we find. Now the thing about this game is that it's highly unfair if you haven't studied statistics, or you don't really have that intuition that makes you good at that really helps. That comes from kind of just paying attention from things. Okay? But this is a game. Suppose I say, hey, let's play a game. Okay? I've got here 7 cards. Got 7 cards. Regular playing cards. Don't care about what's on the faces. What we care about is the color. Got 7 cards. I've got 5 red cards. Sorry, I've got 5 black cards, so diamonds and hearts. And I've got 2 red cards. Okay, 5 black cards and 2 red cards. And before I forget, let me share this code. 5 black cards, 2 red cards. This is one of my instructor's favorite activities when it got close to Halloween, which was to present games like these in his security class. And that should give you a hint here as to what way this is going. Here's the rules of the game you're playing, which is that I'm going to lay these down face down in the table in front of us. Okay, so we've got 7 cards like this. Card, 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 card. You don't know what color they are, but they're all mixed up. Okay, we're going to shuffle them all. Okay? And your goal is to flip over 3 black cards without flipping over any red card. And I mean, come on, it's got to be pretty easy to do that. I mean, let's think about this for a second. Right? For your first choice, only 2 of the cards are red. I mean, only 2 of the cards are red. So the first time you flip over it, it's a 5/7 chance of you getting it. Your second card, that's 4 out of 7. Sorry, that's 4 out of 6 cards, right? We flipped over a card. You flip over another card. You've got a 4 out of 6 chance of getting that correct. And then for the last card, it's a 3 out of 5. Each one of those is a greater than 50% chance of winning. So you definitely have a better than even odds of winning this game. Where's the lie? Because I have lied here. The odds are not better than 50. Yes? You have to multiply them. This is a rule of statistics that you wouldn't know. That these are not what we call independent events. They are dependent on each other. The fact that you get to flip over your second card is completely dependent on the fact that you flip over your first card. And the fact that you flip over your third card, you definitely have had to win the previous two. So you multiply them together. And so if we do that, let's find out what the real odds of this game are. Okay? And we'll throw around some parentheses here to make for good measure to make sure that we aren't doing anything wrong. I mean, it's probably right, but again, when in doubt, parentheses. Okay? That's your real odds of winning the game. Less than a third of a chance. But how would you know this? You don't know, this kind of math stuff to multiply independent, that you need to multiply dependent variables with each other. Don't even know, haven't even had the chance to learn what the difference between dependent and independent events are. You can probably figure that out based on context, but hey, the answer is we can figure this out with Monte Carlo. We can figure this out by doing this game and seeing what the actual odds are, okay? Now, once again, for simplicity's sake, we will, I am going to make this a bit easier, which is I'm going to flip, I'm always going to choose the same thing for flipping over my cards. I'm always just going to grab the first three cards. We can change that later to always flipping over the last three and see the statistics don't change, right? But the idea here is that any three cards are going to give us the same kind of outcome. And so this is where I have fun with Monte Carlo. We can use it to ask, what are the odds that somebody ends up in jail in Monopoly if they by that rule of if you roll doubles 3 times in a row in your same turn, you go to jail. What are the odds of that occurring? What are the odds of somebody winning a game of Pig straight out? If you play D&D, what's the chance of a first level fighter one-shotting a goblin? Those are statistics. They're kind of annoying, but you can solve them with computer programs. Okay? It's easy to do a lot of these statistics rather than sitting down and sometimes it's easier to do this rather than doing the math. It's also very easy to kind of like parallelize these since it's a simulation. You can just simply, tell like 4 different computers to simulate the game, and then you can get a result by combining the results of all those simulations. So it's very easy to parallelize them. They're very useful. And they're very useful for untangling it if the mathematics are really too complex. Okay? But they're also useful for another reason, which is sanity checking this. Like I just told you this math stuff about dependent variables and having to multiply them. But let's go ahead and play that out. Because again, the intuition kind of made sense. That each of those had a better than 50% chance. So what we're going to do again is that we pretty much for every Monte Carlo problem, you're going to need to import random because there's going to be randomness involved in this. And again, this is a game, so I'm going to call my function game. Or if you're taking notes, you can call it maybe card game or call it 7-card game or whatnot. We're just going to call it game for short because it's easy for me to do this. There's no choices like the other one, so no need to make an argument. And we're going to set up the cards like that. I'm going to go ahead and save this. Documents, GitHub, Classroom, ITP. We are going to do card game sim. Okay. Now this statement over here is pretty straightforward once you just kind of read it. It's one of those things I love about Python that we can do, which is that we can just run it, and what it does, it says, I'd like to this is the replication operation here. So I'd like 5 of this and 2 of this. And then the plus operation with lists is concatenation. So it glues them together to make a list with 5 B's and 2 R's. Very useful. And then once again, what we're going to do is that we're going to make use of random to shuffle it. Random dot shuffle. Now shuffle is an in-place operation. That's why I don't need I don't need to return anything. It says shuffle a list X in place, return none, cards. And you'll see here that now the list is out of order, or it's got a different order every time I run it now. Well, it's a bit hard to see because, again, the R's and the B's, they look so similar to each other, which is annoying. Let's go ahead and switch that to be lowercase b and lowercase r to make that a bit easier to see. Bit easier to see now. Okay. So we've got this. And the statistics for, and again, what we're going to do to check if we win is that we got to pick up 3 cards. Now we could make use of random. I think there's a few different things random has. Random dot choice is pretty awesome. It chooses a random element, but it chooses something. Essentially, this is called like selection with replacement, meaning you choose something and you put it back. There's also random dot select, I think, or there's one for there's random dot, let's see, uniform? No, not random dot uniform. Random dot bit choice, Gauss, rand bytes, rand range. Random dot sample, that was it. Random dot sample can choose k unique elements from a population count, which what we'll do is we'll leave that for later. Okay. We'll leave that one for later. But for right now, what we're going to do is we are going to just simply just select the first 3 cards. We're always just going to choose the first 3 from left to right. Okay. Choices is equal to, I know it's super unexciting to do it that way, but choices is equal to cards. And then what we're just going to do is we're going to slice. We're going to just take a slice over here. Okay. I'm going to do cards from 0 to 3, so up to but not including index 3. So we're going to choose the first 3. Okay. And now we just simply ask ourselves if let's go ahead and print that out. We can go ahead and print this out each time to kind of see choices. Right? Black, red, black. Red, black, black. Black, black, black. So that would be a win. Black, red, black. Black, red, red. Red, red, black. Black, black, black. I mean, again, technically in statistics, as soon as you hit this, they would, in real life, when you hit the first one, you wouldn't continue on and draw the other ones. But for statistics, you have to continue. You have to continue drawing the other ones to kind of get your outcomes. Okay. Let me just test random not sample because I don't use that one too much. I know it's used for random with replacement, I believe. Sample, random not sample. Let's see. Actually, that was in the right places. Choices is equal to random not sample. I don't even know if I'm going to use it correctly. Cards, 3. Okay, it looks like it worked correctly, but I'll be able to comment that out. Okay, so now we've got our choices, and very easy to tell whether we win or lose. If I'm just going to do it as I'm going to go ahead and simplify it rather than doing an if-else statement. I'm just going to return return red in choices. That returns a Boolean. It's equivalent to me just saying, it's just a short way of me saying the more readable, if R in choices, return true, that should be return false because I lost. So maybe sometimes it is better to write it out fully so you can find those mistakes. So if I had a red, I lost. Else, return true. Okay. Print out the game to see that we are going to get some results now. False, true, false, false. So now let's go ahead and do the Monte Carlo portion, which is we're just going to go ahead and run this game a bunch of times. For in range, okay, for in range trials, which I did not declare yet, so I will simply go ahead and declare my other variables up here. Trials is equal to 1,000. We're going to start with 1,000. And then we're going to do wins, because again, we're looking for wins, is equal to, right? And then what we do is we simply say, hey, what is the result of the game? The result of the game is equal to call the game function. If result equals true, or we can just simply if result. So if true, wins plus equals 1. And then again, once again, wins over trials. And that kind of, if we scroll back up, that's 0.281, which I had 0.285 here. Now, it's never going to really line up exactly with the mathematically perfect option because randomness, we're throwing randomness into this. But the more trials I do, so if I do 10 times more trials, I'm going to get another digit of precision here, 2872. So very close. Well, maybe not an entire digit. We'll see. Depends on the game. 286. Now you know why I said, hey, we only want to have trials in one place so that I can run it. There we go. 28605. That's getting fairly close to 28571. Monte Carlo's never really is. You have to get the numbers really high in order to get your approximation really accurate. It does depend on the game, but yeah. Now let's go ahead and just go back to doing 10,000 of these. Instead, do this operation instead, which is just simply select 3 at random from with replacement, and we get the same result. 286, 288. But we get the idea that it's about a 28% chance of victory here. Okay? All right. Everybody kind of just follow how that worked. Don't worry, I'll be sure to upload it on GitHub and put this video on YouTube as well. Okay? Games in the past games I've done in the past have included the aforementioned Monopoly question, which is what is the chances of getting an extra turn, what are the chances of getting 2 extra turns, and what are the chances of getting 3 extra turns and therefore going straight to jail in Monopoly. The rules of Monopoly is that if you roll doubles, in other words, you roll 2 6-sided die, and if they have the same result, you get to roll again. It's in the rules. People don't read the rules for Monopoly. Monopoly games create a runaway are pretty vicious and create a runaway winner. And most of the made-up house rules simply have the issue of elongating the game, making it take forever. There should be basically a clear runaway winner in the fairly early on in Monopoly. It's kind of the point of the game. Okay. So one thing you can do with if you're into finance and stuff and want to try your hand at predicting stock prices, guess what? Monte Carlo approximations. So you might want to take a look at this, where you try to predict Apple stock prices using Monte Carlo. This is not something we'll do in class, but hey, if you're interested in like trying to do stock predictions as your final project, go for it. It's definitely a thing to put in your portfolio. Okay, the portfolio of things you want to send to your employers, not your portfolio of investment. So anyway, now we're gonna go and do something a bit more pretty here. Okay. Let's see. Oh, it always takes me a bit of rehashing to remember, but I've always got a copy of it. All right. So pi is an irrational number, meaning it goes on without repeating. There's no simple fraction, right? So we've used the various approximations for it. We've used the Leibniz formula for approximating pi during like the third or fourth lecture of, like the fourth or fifth lecture of class, where we did infinite sums. The Monte Carlo, though, version of this problem is a lot more fun. The idea here is that we are going to be throwing darts at a dartboard. Okay? Many of the darts are going to hit the dartboard, and some of them are going to miss. Okay? And the idea here is that, here we need to get the whiteboard up, because otherwise it's not going to be easy for you to kind of understand. Because, here it is. Okay. And so I apologize for all this tapping noise that's going to be on the recording. It just happens because that's what's going to happen with the pen. All right. So let's see. Yep. Unit circle, radius of 1. So what we're going to have is that we are going to have our dartboard. Let's see. No. Enhance inked shapes. There we go. I don't need that. Instead, what I need is this. There we go. So we have a dartboard. It's pretty nice to be able to do that. Let me try to get it a bit better and then zoom in. There we go. That's more towards what we have. We're going to have a dartboard, okay? And we're going to go throw darts at this dartboard. The circle represents the dartboard. Got it? And the box represents basically kind of the entire universe of being able to throw a dart at the dartboard. A dart's never going to land outside of this dartboard. It's only ever going to land inside this dartboard. Make sense? Now the idea here is that we can look at. We've got this interesting trick here that we can look at the measurement of the number of darts we throw on the dartboard, okay, divide by the total number of darts, and that can actually give us pi. It's pretty cool. So let's go ahead and describe what we're simulating a bit more precisely, okay? And you'll have to forgive me, there's a bit of math, but it should be math that you're familiar with, nothing more than some algebra here and the Euclidean distance function, okay? So our dartboard is going to be the unit circle. The unit circle, as you remember, means that that dot here is 0, 0. And this unit circle has a radius of 1. Got it? So if this unit circle has a radius of 1, how big are the sides of the square? So if the radius is, 2. That's right, 2. So this is going to be and the radius happens to be the diameter. And the side of the square also happens to be exactly as long as the circle's diameter, right? Just happens. Some happy coincidence there. Okay. So right, this is entirely that. Come on. Ugh. I don't know why this sometimes gums up. All right. So what we're going to do is we're going to simulate the throwing of these. We're going to have this square acts kind of a magical force field that's going to make sure that everything lands in here. Okay? And what we're going to do is that to simulate throwing darts, we're going to use random again. We're going to choose a random number between -1 and 1 for the x-coordinate and -1 and 1 for the y-coordinate, right? Because if you remember, if this is 0, 0, then this corner is 1, 1, and this corner would be -1, -1. Everybody following me so far? Right? I mean, I'm not going to put it on a graph formally. Okay? So so there we go. So it's going to land somewhere in there. Okay? Now we will know the dart lands in the circle based off the distance formula. It lands in the circle if it lands, so how do we know if it lands in the circle? Because we could see it. How would we mathematically know? If the distance from the center of the circle to the dart is less than 1. Why? Because it has a radius of 1, right? The circle has a radius of 1, so if it's greater than 1, it's going to land out. If the distance from the center is greater than 1, it's going to land outside the circle. And if it's 1 or less, it's going to be inside the circle, right? That's how a circle is defined, a distance from the center of it. The radius is. So how do we calculate how far something is from the center? We would say x squared plus y squared and take the square root of that to get the distance. That's the Euclidean distance function. That is the hardest bit of math we have today. Okay? Okay? So now, since the area of the circle, okay, we can figure out how big this circle is, by the way. Right? The circle has a radius of 1, right? So the area of the circle is what? It's pi r squared. So radius is 1, so the math becomes really easy. The radius of the circle is just pi. And the area of the 2 by 2 square is 4. So we've got pi being is the total surface area of the circle. 4 is the total surface area of the square. So the number of darts that land inside will get closer and closer to pi, and the number of darts on the outside, well, what we could do is just simply take, or rather what I should be saying is that we've got the number of darts that we're throwing at it, the number of darts that hit over the number of darts that we've thrown will get closer and closer to pi over 4. Okay? And the best part of this is that we'll visualize this. We're not going to do this as a dry mathematical thing. We're visualizing this today with turtles. Okay? So what we're going to do is we are going to do let's see. Let's see. I always forget this part. Turtle docs, Python graphics, win dot, set world coordinates, right? Which is how the okay. So import turtle. Turtle.setWorldCoordinates. -1, -1, 1, and 1. And I'm just going to test this out. Bob is equal to, plenty of time. Turtle. Bob.goto 1, 1. Right now I'm just testing this out to make sure that I've got the syntax right. Yes, I did. Okay. So what did I just do? What I did here is I said, hey, set the world coordinates to -1, -1, 1, 1. What in the world does that mean? Well, what I've set is the drawing area. Okay? All I've done is I've set the drawing area. This is what went on in your hurricane thing to turn it into to make it longitude, latitude. What I said is that the drawn area, instead of being, whatever the window happens to be, I want it to zoom in a bit. I want the bottom left corner That's what these two coordinates to be negative 1x and negative 1y, and the top left corner to be 1x and 1y. So over here we've got negative 1, positive 1, positive 1. So there's our square. There's a square. Okay? So now what we're going to do is that we are going to, I'm going to write a function, okay, called def throw dart. Okay? The other thing I need to do is import random because we're going to be throwing stuff at random. And we're going to be throwing Bob, sorry Bob, we're going to be throwing Bob at the dartboard. Yeah. So let's go ahead and so what we have to do is we have to generate a random x coordinate and a random y coordinate to figure out where he's going. Okay? So x is equal to random dot, and let's go ahead and open up, I'm going to go ahead and open up my idle over here just to kind of test to make sure I'm getting the syntax right. Import random dot rand, let's see, is it range? Choose a random int. No, it's, I bet I know what it is. It's random dot uniform, I bet. Random number, yeah. Random dot uniform negative 1, 1. Okay, and that will choose a random number uniformly. Yeah, there it goes. And that chooses a random number uniformly at random, meaning that any number is equally likely than any other number. And just to kind of remind you, there's an infinite number of numbers between 0 and 1. But this will choose from that one, any result equally likely as any other, a negative or positive number. Between negative 1 and 1. So random dot uniform, that's how you do random floats. You're probably never going to see it after this lecture. It should let you know how infrequently I use it by the fact that I have to remember it specifically for this lecture. Okay, so uniform negative 1, comma 1. That generates a random x. Y will also generate a separate random number. You don't want to set them both equal to the same thing, so you have to generate a random number for both of them. Okay. So we've got that. Okay, and then what do we need to do? Let's go ahead and I'm going to move the creation of Bob up to the top again, just the top, and I'm going to set Bob dot speed to 0. We're going to do something else later to speed up the animation. Bob dot speed 0 to set his speed to 0, and then we're going to do Bob dot up because we don't want him to draw. We're going to be doing everything with stamps to represent hits. Okay? So what we'll do is that now that we know that it'll always be up, Bob, we generate a random coordinate. We tell Bob to go to that coordinate. Okay? Bob dot go to. Okay? X comma Y. Very simple there. So throw dart Bob. Okay, and what I'll do over here is I'll go ahead and actually put in a for loop. Trials is equal to 100. Now we'll do 10 first. For in range trials, same format as what I've been doing. There's a reason why I do it like this. We're going to just simply do that. We're not collecting our data yet, but we're able to see from this point. Okay, let's see. Is it still running? Did it go? What did I do wrong? Oh, I forgot to say stamp, right. Bob dot stamp. Thank you. I was trying to make out what you were saying. So now we'll tell him to move, and now he'll stamp, and now we've got some dart throws over here. And if we like bring this up to 1,000, we'll be able to kind of see that happen. Although that's not really going to be useful because actually it will time out with all that. We'll keep working while it's going. But it did suggest a way of dealing with the timeout, which we'll take a look at in a bit. Okay, but this really doesn't tell us anything whether it hit or not, right? We're just seeing Bob just kind of jump around randomly, which is pretty cool, but it really doesn't tell us anything. Let's go ahead and set Bob.shape to be a circle. I think that's going to be probably the best choice here. Save and run. There we go. Okay. And now what we're going to do is that we got to detect whether or not we're hitting or not. That's what we're going to return, whether or not we hit. Okay. So how do I tell if I hit? I figure out what the distance is. And the distance is the distance from the center, right? And now remember the Euclidean distance equation for 2 dimensions is fairly straightforward. It is just simply your x squared plus your y squared and your square root. I guess we'll have to import math as well to do the square root, but that's about it. So d is equal to math dot square root of x squared plus y squared. Super easy there, right? Super easy to just calculate the distance. And now, so now let's actually, before we do anything with it, let's go ahead and do our if-else statement. If d is less than 1, that will be a hit. Should blue or red be a hit? What? Red's a hit? Okay. If d is less than or equal to 1, red is a hit, that will be red. So Bob dot color red. And I'll have to move the code around a bit. If it's not a hit, it's a miss. Bob dot color blue. Okay. I'll move the stamp down behind that. Timeout exceeded. That's fine. And then we will go ahead and run this now. So now we're starting to get hits. The reds represent where we landed inside the circle. And the blues represent that we landed outside the circle. But that's not really doing too much for us right now. It's certainly going very slow. But we can slowly but surely see that we've got the outline of a circle occurring. Right? Very slowly. Time's out. So it says, recommend this for faster animation, which basically says I'm going to skip drawing every so often. And by every so often, it means a lot. So what we'll do is that we'll say, take this, we'll use tracer, which really was going to speed up everything. And then we get to see basically that this distance function works for getting reds. So we've shown that this kind of works. Okay, now let's actually collect data. Okay. By the way, like the Leibniz function, this is a really bad way to approximate pi. You have to have a very high number of trials in order to approximate pi. So here what we're going to do just simply is, again, return d less than equal to 1, because that will return a hit. And so again, what we'll do is we'll simply take hits is equal to 0. I will say results. Sorry, I'm going to simply say result is equal to throw dart Bob if result equals true. Hits plus equals 1. So, if I threw the dart and it hit, awesome, then the number of hits goes up. And then we will return. And then we'll print. So then I'm going to print 2 things. I'm going to print out hits over trials. And then, because that's not really going to tell us anything useful, hits over trials. unless we have something to compare it to. Print math.pi over 4. Why? Because the ratio between the area of the circle and the area of because the hits over trials will approximate the area of the circle, the ratio of the area of the circle to the area of the square. And we know that the built-in assumption for this is that the area of the circle is pi and the built-in area of the square is 4. Just from the kind of parameters we set up. Still taking a bit too long. Turtle dot tracer, what does that do? Tracer, delay, so non-negative integer, on, off, or only the nth. Okay, so if I update that to like 50, is that going to go a lot faster, I bet? Yep, it goes a lot faster. And so 798, print math has no attribute pi in capitals, so I bet you it's just pi. And there we go. 0.786 to 785, or we can just simply make this a bit easier for ourselves and print out math.pi and multiply this by 4 to go from pi over 4 to 4. Sorry, pi over 4 to just pi. So now, 3.14159 obviously is pi, and we've got 3.156. Not great, not terrible, okay? So now let's go ahead and see what happens when we up the trials. Let's go and up it to 10,000, and we'll be able to see. Does a very good job of approximating that circle, right? And the weird edges, of course, is because what I'm drawing with are circles. And there we go. That gives me 3.1176. Gives me more digits, although, again, like I said, this is a not great way to approximate pi, but boy, is it an amusing way. This is a Monte Carlo approximation. Let's go ahead and do 500, save and run. There we go. There we go. Can I do 10,000? And 5,000 over here. What does that do? It's not really going to speed that up at all, is it? Okay. Now, it's skipping the animation a lot. There we go. So 3.14012. So there you go. Share code. That's pretty cool. I personally think it's very cool. So again, this is just what we were doing here is we're just simply throwing darts and comparing the number of hits that land in the circle and the number of hits that land in the board. And what we did to get pi over 4 is we just simply deliberately chose the distances such that the area of the circle would be pi and the area of the square would be 4, allowing us to approximate pi over 4 because the ratio would it would approach the ratio of pi over 4, the number of hits over the number of throws. Okay. Monte Carlo approximations are great. I love them because they allow me to ask you here's a game. Can you simulate this game on an exam? It's a lot of fun to be able to do that. There are also, again, the last topic that I'll be teaching you, the last guaranteed to be on an exam topic I'll be teaching you. I only really have one other kind of thing on the schedule after we assign the final projects. Well, we have Git, but that's not in the exam. But we also, for the final projects, have, after that I'll do regular expressions. Regular expressions will be on the final exam, but the way, again, the final exam works is that I'll give you a bunch of big questions, and you choose a subset of them. If you don't feel like you have the mental energy to study another topic, then don't, and just don't select that as one of the options. But if you do devote, 2 or 3 hours learning regular expressions, one, you learn a super useful skill that will serve you outside of programming, because pretty much every text editor supports regular expressions these days. And 2, easy 20-ish points on the exam, So keep that in mind. So that is all for today's lectures. On Tuesday, I plan on talking a bit more about the final project in preparation for that, the homework that is upcoming, which is PIG, and then finally, I plan on also doing more Monte Carlo approximations on, well, not Monday, but Tuesday. You get the idea. Have a great weekend.